Okay, I think we're live. So I'll just briefly introduce our speaker for this session. Professor Balraman Ravindran is the Mindtree Faculty Fellow, Professor at the Department of Computer Science and Engineering, and Head of the Robot Bot Center for Data Science and Artificial Intelligence at the Indian Institute of Technology, Madras. He completed his PhD from the University of Massachusetts Amherst, during which he worked on an algebraic framework for abstraction and reinforcement learning. More recently, his research interests have ranged from spatio-temporal abstractions and reinforcement learning to social network analysis and data mining. Having co-authored over 200 conference and journal publications, Professor Ravindran is widely seen as India's foremost reinforcement learning expert. He is the recipient of the Mindtree Faculty Fellowship and Yahoo Faculty Award, among many other awards. Professor Ravindran has also taught a very popular reinforcement learning course, which you all should definitely check out online if you haven't already. So thank you for taking time off your schedule to be a part of this event.
Uh, so, so thank you, Jay, and good afternoon, everyone. And it's a hard time, to come to any talk, whether it is live or on video. So let's see if I can keep people engaged. So what I'm going to talk about today is influence maximization in unknown social networks, right? And how to use reinforcement learning to learn policies for effective sampling on graphs so that you get to discover some parts of the social network before you run influence maximization on it. So there are a lot of terms here in the title, and hopefully as we go along, I'll explain all of these to you. So before we begin, I just to start off with, I'll be giving a very brief introduction to what reinforcement learning is, and to the extent possible, I will try to avoid as much math. So people who have been watching the previous talk can take a slight breather. And so I'm going to try and see how I can do this more from an institution level, right? So all of you are familiar with machine learning, right? So the goal here is to learn functions from input to the output, given a lot of training examples, right? To basically optimize some kind of an error, and then you learn a mapping, right? This is the traditional supervised learning paradigm. But usually the way question I ask is, hey, how did you learn to cycle? Did you learn to cycle from data? I mean, if I had shown you like hours of videos of people cycling, could you have just gotten on a cycle and done it? Can't, right? So you have to try things out. It's a trial and error process. You have to get on a cycle and try to move and fall down, get hurt, and so you get some kind of feedback. You know that you're doing something wrong if you fall down and you get hurt. And if you're a kid who is learning to cycle, you have your parents applaud and tell you, hey, that's a good job, and so on and so forth. And therefore you know that you're doing well. But nobody really tells you what is the exact thing that you have to do in order to stay balanced. Right? I mean, people can tell you things like, hey, stay balanced, but that doesn't really help because you don't know what we have to execute to stay balanced, and we have to try it out. And it's not just learning to cycle, and a variety of things, like, I mean, as babies, however, babies learn to talk, walk, everything. A lot of human learning does happen through this kind of a trial and error process. And reinforcement learning is all about formalizing this trial and error learning into a mathematical framework and coming up with algorithms that help you to achieve this kind of trial and error. That's a very simple uh, uh, um, description of what RL is. Let's go back and look at more carefully, right? So let's take the example of tic-tac-toe. All of you are familiar with tic-tac-toe, I presume. So you start off with this 3x3 board, and you have to get 3 pieces in a row, right? X's or zeros, right? And so it's a supervised learning mechanism, right? So how would you do this? In supervised learning, so you'll be given this kind of board positions, right? So, and then an expert would come and mark out saying that, hey, these are the moves you should play if this is the position you find yourself in, right? So if this is the position you find yourself in, these are the moves that you play. So this is essentially an expert would be giving you many such examples. And from these examples, you learn a policy to play the game, such that given any position, you're able to make a response to that. Right? So this is how supervised learning would work. On the other hand, the trial and error learning mechanism, right? Reinforcement learning will just say that, hey, just play, right? Play the game. If you win, I'll give you 1 point. If you lose, I'll give you, say, -1. And if you draw the game, I'll give you 0 points, right? And you have to just learn from repeated play. I'm not going to tell you how to play it, but I'll tell you what the outcome whether it's a good outcome or a bad outcome, right? So that's basically the way you learn to play tic-tac-toe through reinforcement learning. It sounds a little daunting, uh, uh, but you can learn, right? So let's see how you would do this, right? So let's say that this is a game that you have played, and so at every point of time, this is what is known as a game tree, right? You start off with all blanks, and then for every possible move that you could make, there is a branch in the tree. So therefore, at this point, there are 9 branches, and then subsequently you have the possible responses your opponent can make, and then your moves, so on and so forth, and then you come to a point where this is the final board position here, where you have won the game, right? Now, once you win the game, what you can do is you can go back and look at all the moves that you have made in the course of the game and say that, hey, all of these moves are good moves because they let me win the game. Right? So the next time I come to a position that is very similar to, say, this position, right, I'm going to increase the probability of taking the move that I just did. Make sense? If I come to the same position that I saw in this game, then I'll more likely to play the move that I played in this game than another move. Okay. So this is how I do it. So once I go and play a game, and if I win, I go back and look at all the moves that I made and increase the probabilities of those moves. Right. But what do I do if I lose the game? Right. I go back and decrease the probability of all the moves. Right. And if I draw, I could do multiple things. So the easiest thing to do is just to leave the probabilities unchanged. Like I'll just play the same thing again. Right. So I'm not going to increase or decrease any probability. Okay? So that's essentially the learning algorithm, and it works actually. You can see that if you repeatedly do this over many games, you actually start to learn to play a very decent game of tic-tac-toe. Well, this is assuming that your opponent is not a perfect opponent. As you know, you can never win against a perfect opponent. Okay, but here is one thing, right? So let us say that this is one of the positions that you encounter before the game ends, right? Now, my question to you is, do you really have to wait till the game ends to know what the outcome is? Not really, right? Because once you get this kind of a position, you know that the X is going to win. Right? Either X can win by putting the next move there or here. There's nothing that zero can do, O can do that will stop both these outcomes. Therefore, once I come to a position like this, I know that I have won. Right? So X can just go back and increase the probability of putting a X here, right? And then increase the probability of putting the X here, and so on and so forth. So it can basically just do whatever it did, right? When it knew that it had won the game, just because it's come to a position where it sees it as won the game. Okay, is that clear? So you don't have to wait till the end. But then, how did I know that this was a winning position? Right? I knew this was a winning position because I knew the rules of the game. I did some kind of reasoning here to figure out, hey, given that these are the rules of the game, there is no way that my opponent can win from that. Correct? But then that's fine for tic-tac-toe. What about more complex situations, more complex games like Go or chess or non-game scenarios, right? So how would you do that? So remember that you're playing this thing many times. So you have the past outcomes. So what I can do is I can just remember, okay, whenever I have seen this position in the past, right? What is the likelihood that I will win from here? What fraction of the games have I won from this position in the past? Right now, if I go from a position that where I have won, say, 40% of the games, to a position where I have won, say, 60% of the games, then I can consider that move as a good move. Right? So I don't have to worry about actually waiting till the end. Okay, from 40% winning position, I've gone to a 60% winning position, or I've gone to a 90% winning position. So that's a good move. So I'll increase the probability of that move. Or if I go from a move that has a 40% chance of winning to something that has a 10% chance of winning, I'll say that's a bad move. Then I'll decrease the probability of making it. So in some sense, I don't have to wait till the game ends because tic-tac-toe is nice. It ends in 9 moves or 5 moves from your point of view. But in other more complex scenarios, the game could just go on forever, right? So you would like to be able to learn as you are progressing, as you are learning the game, as you are playing the game, not just wait till the end of the game. right? So this is essentially this way of learning where I'm using the predictions at t plus 1, right, in comparison to the prediction at t, and using that to change my behavior is called temporal difference learning. And this is the one of the core ideas behind a lot of reinforcement learning. This was originally proposed by Bartos and Anderson back in '83, and somewhat in many cases is regarded as the starting point of the modern RL literature. Okay. Um, Sorry, I should have asked this question earlier, Ajay. How do questions work? Do people ask questions in the middle of talk, or do they do it at the end?
We normally have questions at the end of the talk,
Okay,
for
sure.
moderated questions.
Sure,
But
great. So,
yeah,
then I'll just keep going. I'll wait till the end of the talk for questions. Okay. So reinforcement learning has just not been studied in AI, but it has had profound impact in other areas like behavioral psychology and neuroscience as well, right? And and why are people so enamored with reinforcement learning more recently? The last 10 years or so, reinforcement learning has really picked up steam, and that is mainly because reinforcement learning has had some several huge successes. Right, reinforcement learning really works. So whether it is playing non-trivial games like Go, or being very good at chess, or doing real-time strategy games, right? Or whether it is robot control or flying helicopters. And here is picture from RL doing power control and helping Google save up to 40% of power bills in data centers. Or even more recently, looking at things like protein folding and doing better than humans in protein folding. So there are many cases in which reinforcement learning has had phenomenal success of late, right? And therefore, more and more people are now paying attention to RL, right? So before we dive into the actual meat of the talk, I would like to just take 1 minute and tell you that what are the essential components that you need to understand to say that you're designing a reinforcement learning solution for a problem. Right? So you need to have three things. The first is known as states, right? So in the tic-tac-toe example, you needed to know what the current position of the board was, right? So where are the X's and O's before I can make a move, right? So a state is a description of your environment so that you have enough information to take decisions. Okay. So the raw inputs are often not sufficient. I mean, if you're just having a camera and taking images, or when you're playing video games or something like that, the raw inputs are not sufficient. You have to do some kind of processing. So it could either come from pre-processing, or the more modern way of doing that is to process the inputs through a deep neural network, so that you get some kind of an embedding, or a vector as an output, and that vector is used now as your state information. Okay, so this is enough signal for you to make your decisions on. So this is the first part, right? I mean, all three are non-trivial, and you'll see as we go along, and we have to work on all of these three to address this network discovery problem. The second component that you need to design an RL solution is what is the granularity at which you're going to control the system. Right? What are the control variables? Right? In tic-tac-toe, it is pretty easy. They're basically the moves in the game, right? But then in cycling, what is it that you're talking about? I mean, just looking at the way that I'm holding the handlebar, the direction that I want to move in, or is it more fine-grained actions, right? Like how much pressure to give on my legs, I mean, my left leg versus right leg, and how much do I twist the handlebar to turn it? So what are the actions, right? So it could be discrete, right, like moves in the game, or it could be continuous, like torque motor, and so on and so forth. So you have to decide what is the granularity at which you want the actions to be taken. And the final thing is the what is called the reward. This is essentially the feedback that you're getting from the world, right? So in tic-tac-toe, again, we said that you get a +1 if you win, or you get a -1 if you lose, right? That's the score. And that's essentially the reward of the problem. It typically tries to define the goal of the problem and not really tell you much more about it, right? And not tell you what the solution should be, right? It tells you what are the goals and what are the constraints sometimes are conveyed through the reward. So these are the three components that you need to really figure out in order to design a reinforcement learning solution. Okay. So this ends my RL intro. So now we jump into the actual cream of the work. And so this was a joint work with Harsha, Priyesh, Brian, myself, and Milind. Milind is, of course, very popular and actually an alum of which. So he is a faculty at Harvard and heads the Google's AI for Social Good initiative, Google Research AI for Social Good initiative. So Harsha was a master's student with me. Now he's going to Georgia Tech this year whenever they open for his PhD. Priyesh was a master's student. He left to McGill last year. And Brian is a senior PhD student at Harvard who is just winding up. And this was work that was presented at AMAS 2020. And so you can look it up in the archive link there. So what is the influence maximization problem? So there are many components, like I said, right? There is influence maximization, then graph sampling, policy, so on and so forth. So the influence maximization problem is given the social network, right? Pick certain influencers, right, or peer leaders who can help disseminate information to the maximum number of other users on the social network, right? So the way we typically look at a social network is like a graph, right? So here is an example. So each of these nodes here, both the blue and greens, are people in the network, right? People in some kind of a community. And an edge in this graph means that these people are connected to each other. They know each other, they influence each other, and so on and so forth, right? Now, here is a simple example. I'm going to say that a person gets influenced, right? So maybe he believes a piece of information, right? Or he goes out and buys a new product or something like that. If at least two of his friends or two of his neighbors on this graphs are already influenced, right? So here is how this dynamics will work. So the blue nodes are the ones that are already influenced on this graph, right? And now, if you look at this, and these are the set of nodes who have two neighbors who are influenced. So they turn, okay, they now go and whatever, buy the item or believe a rumor. And now this is going to cause a few more nodes to get influenced, and then a few more, and now the whole community is influenced, right? So now the goal of this influence maximization problem is, given a graph, like you saw in the previous slide, right? Select k nodes. There we selected 4 nodes to activate, such that the information flow across these edges, right? At the end of this diffusion process, the maximum number of nodes have been influenced or have received this information. Get that? Right. So given a graph G, select k nodes to initially influence or activate, just that at the end of this information diffusion process, the maximum number of nodes have received this information. Of course, if I don't have any limit on how many nodes I should activate, then the problem is easy. But typically, you have a hard limit that's due to all kinds of constraints. Say you have a small number. Suppose you might have a graph with hundreds of nodes, but you can influence only, say, 5 people to begin with. And then you have to pick those 5 very carefully so that you have the maximum spread in terms of this information reaching a lot of people. So this is found, in fact, our motivation for doing this was to look at HIV prevention among homeless youth. Right. So in Los Angeles, where Milind and his group were earlier, so they were working with some of the governmental and quasi-governmental organizations, where they were trying to identify homeless youth who, if they convince them that HIV prevention is an important issue, then they will go around in their community and convince enough people to come in for more information, testing, and so on and so forth. So the main problem was that because of ignorance among the youth, there was sudden surge in HIV cases among homeless people. So there are a variety of other things. People have used this kind of influence maximization procedure to study substance abuse interventions, both in drug interventions and substance abuse interventions. In that case, in HIV prevention, and also in microfinance adoption. The microfinance study was actually done in India, in Karnataka, right? And typically, people use some kind of a greedy algorithm. So to minimize the Kempe, Kleinberg, and Tortosh algorithm to minimize the computational cost of this influence spread, right? So how do you pick the k nodes, right? If you use this kind of a greedy heuristic. But the problem when I'm working with this kind of real world social networks, right? So the problem is the given the graph G, right? So the KKT algorithm starts given the graph G, right? And but you're not given the graph G, right? We have very little data on the structure of the social network, and so you have to actually go out and collect the data. You have to figure out what the network is, because homeless youth don't register themselves on Twitter or Facebook and then identify themselves as homeless youth, and so it's very hard to crawl the data from somewhere online. So you have to go actually physically ask people, right? And we have to operate with a budget, very tight budget, even for how you query the network. I mean, there are two budgets now. One, what is the k that you pick to influence, but then what is also the number of nodes that you can query in order to discover the network, right? So now the problem breaks up into two parts. So there is a network discovery part, where we start off with some nodes that we know in the graph, and then you run a network discovery algorithm where you query nodes to discover the unknown parts of the graph. And then with the discovered graph, you run your influence maximization algorithm. Okay, so is it clear? Now the network, this is where the network discovery for influence maximization comes. So I motivated influence maximization first, but then you don't have the graph, right? So to get to the graph, you have to run this network discovery phase. And then people have used multiple heuristics to solve the network discovery problem as well. And what we do in this work is to set it up formally as a reinforcement learning problem, right? And then try to solve the network discovery problem. Okay. So remember what we need to do: states, actions, and rewards. So the states are the current state of the discovered graph, whatever it is, right? The actions are all the nodes in G that have not yet been queried as to who are their neighbors. Okay, the actions basically you can pick one of these nodes and query them. Hey, who are your neighbors in the community, and then you can add them to the graph. And the reward is at the end of the number of queries, right? So you'll have some kind of a discovered graph, and I run influence maximization on that discovered graph. Okay, and then figure out how many people do I actually influence in the real graph, not on the discovered graph. How many people I influence on the real graph, right? That is my reward. Okay. It's a little complex process, so let us see if I can explain that with this picture. So I start off with the graph, right? That's the graph. All the nodes in white are not known to me. All the nodes in white and the edges that are incident on those nodes are not known to me. All I know are the nodes marked in gray, because they are marked in gray because I know their entire neighborhood, so I don't need to query them anymore. And the nodes in red are also known to me, but I have not asked them any query, so that I don't know who their further neighbors are. Okay, so now this is the state. So I have to somehow encode this graph into a state vector. And then the reinforcement learning agent selects a node B. Let us say that the reinforcement learning agent has selected that node. That is the action it selects. So the possible actions the RL agent can select are all the red ones, right? The whites are not known to it, doesn't even know they exist. And the grays are all been exhausted, right? Only the reds are the things that could potentially select, right? Now it selects a node. Here we mark it B, and it queries the neighbors, right? So the nodes marked in dark brown are the answer that the light brown nodes return. Right? The light brown node is the one that was queried, and it returns these things as possible neighbors. Okay. Now, if the number of queries you have done is less than your budget, right, then you go back with a new graph, and then you try to again do the same thing, right? But that is a new graph you have. So the less than the query. Now you go to the new graph, you notice that the original node that you queried, the light brown node, has now become a gray node because it's exhausted. But the neighbors that you had queried now actually show up as red nodes in this new state. And remember, you still don't know these white nodes exist in the graph. If you're less than the query budget, you update your state and you continue querying. But if you have finished your query budget, you're exhausted the query budget, then you take all the nodes that you have discovered, right? So the red ones, the gray ones, the light brown, the dark brown, so all of these together will constitute your discovered graph. And what you do is you run influence maximization on just this graph alone. Right? Now pick 3 nodes that are the most likely influences or the best peer leaders, and then start your diffusion process from them. Right? And then let us say that, you remember I showed you initially how the diffusion process runs. And so at the end of the diffusion process, you count how many nodes in this full graph, right, were influenced. Of course, you wouldn't know nodes that were not influenced, whether they exist or not, but at least the nodes that were influenced, because in this case, it was spreading HIV information, right? So you count the number of people who come in to get themselves tested for HIV and count those as the people that have been influenced, right? And based on that, you'll give a reward signal to your RL agent. Okay. I hope that makes sense. So you start off with your current known state of the graph, right? The RL agent picks an action, and then you query the node for its neighbors. And if you're within the budget, you just add it to the discovered graph and keep going on this loop. If you've exhausted the budget, you take the graphs that, I mean, the part of the graph that you have discovered so far, run influence maximization on it, and then compute the reward. Okay. So just to remind you, this is exactly what we do. So states, actions, and reward. Okay. But the main problem is, remember that reinforcement learning needs multiple iterations, right? And so we really don't have the access to the actual network to run multiple iterations on it. Typically, you have to run this on a zero-shot case, right? When you're given the real social network, if I go to LA and I have to figure out who are the delinquent youth or what kind of a network they have today, I can't assume that I can run this multiple times. I have to look at some kind of past data or an equivalent data generated from some other source, right? And then learn a policy on that allows me to generalize across graphs that are similar, right? So that's why we say an appropriate class of graph. I can't say that, okay, give me any other graph, I'll generalize on that, but I need to generalize across the appropriate class of graphs, right? So the typical heuristics that people use make some kind of a priori assumptions about the graph structure. And so what we do is we assume that, hey, there is a way of doing the, discovering the structure of the graph by using some kind of graph neural networks and embedding, right? So this is a slightly complex architecture that we use. I'm not going to get into the details of it. So we use something called the graph convolutional network. So if people are familiar with convolutional networks, you can think of graph convolutional networks or as an extension that is tuned to run on graphs as opposed to a regular grid like you do for images, right? So here it looks at like one-half neighborhoods of nodes in the graph and then try to compute features based on that, right? And so the top pathway is something that computes a representation for the entire graph that you have, right? Remember, this is not the full graph, right? This is not the entire graph, but only for the discovered part, right? So only the red and gray nodes will be participating in the top pathway. When I say adjacency matrix here, it is not the complete adjacency matrix of the graph. It's only the discovered part, right? And then this outputs a vector that somehow encodes the current state of the graph. And then I need to have my actions, right? And so my actions are also encoded in a similar way. And actions here again, remember, are the nodes, or all the red colored nodes, right? So each one of those nodes will get an encoding, and then I pass it here. I pass the state and the action pair. And what I get out is some kind of a utility score that tells me how much reward that I'm likely to get at the end if this is the sequence, this is the action that I pick in this particular state. Right, so that is what this action value, the state action value function is some kind of a utility function. Sorry, some kind of a utility function that tells me how much reward I'm likely to get if I perform this action. So this is basically the structure that we use. And if people who are familiar with some of the deep RL thing, it's essentially a DQN that we end up using. Right? It's a simple DQN, except that the representation is learned from the GCN and deep walk for the nodes. Okay. And we ran experiments on many different data sets. So the one that inspired us to start out the whole thing off with the homeless youth network. So the way these networks were gathered was by looking at earlier campaigns that have been done among the homeless youth. So people have already done this. They are not working in a vacuum. So people have done this. So we get this kind of data sets from what has been done already, right? And so similarly, this is to study diffusion of microfinance adoption in Indian rural households. That again, people have done the study earlier and they have gathered some data. So we have a rough idea what the network should be. And of course, then Twitter, yeah, that's easy to get. Right? So we used some of the Twitter networks that people have already crawled. And then the last data set that we used was on from an animal network. This is basically looking at wildlife. Wolves are like small burrowing animals, and then we look at how if they have been in contact with each other or not over a period of some time. So don't worry about the trap here. The trap here is a camera trap where you take pictures of the dogs. You're not getting them, right? So we also did a bunch of other things. So we don't have too many actual networks for training. I mean, we have like a couple of these, except the Twitter network, we have a lot of, but the other ones, we have only a few networks that we can train on. But if you really want to build something that is robust and generalizable, we needed a lot more data. So what we did was we used structural properties of these networks that we already had, and then generated synthetic data where the graph structure, like the number of nodes, the degrees of the nodes, and the size of the different communities, and so on and so forth, actually match the real world network, right? So given the same theme, but you can still generate random graphs, variations on a theme, if you will. And we used something called the stochastic block model to generate graphs that were similar to the training graphs. Right? And so this is the result. So this is really nice. So there are two things. Let me see if we have a definition. Okay. So there is this percentage increase and the percentage improvement. Okay. So the percentage increase basically takes the best known result out there, right, and looks at how much better than that best known result do we do, right? How much? So that's a percentage improvement. So how much better than the best known result that we do, right? And percentage increase is something little more nuanced. Okay, let us say that I know the entire graph. Okay, and I give you a budget that you can influence only say 3 nodes. What is the best you can do? Okay, so this is one thing. This is assuming that you know what the ground truth is. On the other hand, you run the best network discovery algorithm, right? And then compute 3 nodes on the discovered graph. Okay, so there is this gap in this performance. Let us say one influences 30 people, right? So the one where I know the full network, right? The best thing I can do is influence 30 people, and one where I run the discovery, the best I can do is influence only 20 people. So the gap from 20 to 30 is 10, right? So what fraction of the gap am I able to close? Right, by running the discovery algorithm using reinforcement learning. Right, so these are the two metrics that we use, because just to say that, hey, this one has already had 20 people and I get only 22, but even if I know the best result, if I can get only 23, then 20 to 22 is actually a big jump, right? I've basically covered 60% of the gap. It is not like I have a 10% improvement. So we wanted to make sure that we capture both cases, and you can see that we get really good improvements. And remember that every little improvement is actually one more human being influenced, one more human being that get tested for HIV. So in terms of human cost, right, even like a 10% improvement is considered a big win by the community. Right. So we did a bunch of different things. So here are various results on using real data and synthetic data and so on and so forth. So the results on the synthetic data is not completely clear. So for example, in the rural networks and also in the homeless networks, using synthetic data really helps. But in the animal networks, it is not really the case. But that's also because we have a lot more data in both the retweet and the animal case. So training just on the data alone was useful. Right? But then even the retweet networks using synthetic graphs does help. Right? So these are the results. And next, what we did was we stepped back and we said, hey, okay, reinforcement learning is great. Is there something that we can do to analyze what it is doing? right? Right. So then this was the first set of analysis that we did, right? So we looked at the properties of the nodes that the DQN queries versus change. So where change is the previous state of the art. That was proposed by Millen's group in one of the earlier papers. And we compared these results on multiple things. Here I'm going to show you an example from a retweet network and homeless network. And the two of the properties we looked at is something called degree centrality. That means does the node have a lot of neighbors? And the second thing is between the centrality. Does it act as a bridge between different communities in the graph? Right? So if it's not a single community, if the graph has multiple communities, a node that with a high betweenness acts like a bridge between different communities. So if you want the information to flow from one community to another, then you would like to influence these kind of bridge nodes, right? So we said, okay, these are two important properties. Let's see if how these things operate, right? I'll come to H1 and H2. Okay, I don't have H1 and H2. I'll tell you what H1 and H2 are. Okay. I apologize. I don't have slides on it, but I can verbally describe them to you. Right. So H1 is essentially heuristics that we created from the reinforcement learning policy. Right. H1 says that among all the undiscovered, among all the unqueried nodes, right? Query the one with the least degree. Okay. Query the one with the least known degree. You don't know the real degree, right? So whatever is the degree that you know, you query that. So why is that a good heuristic? If the degree of the node is very small in what you have discovered, and if roughly all the nodes have similar degrees, then there are a lot more nodes that are neighbors which are not discovered. So that's the simple idea. And if the degree is very high already, that means all its neighbors are known to you. The degree is very small. We hope that there are a lot of unknown neighbors, and therefore you'll bring them. Okay, that's one heuristic. And the second heuristic, which is H2, says that hey, do that, but do that only among the nodes that you discovered in the previous round. This is basically more like a line search, you know. So don't go back and look at nodes that you didn't pick up the previous time. Just keep looking at nodes that you just discovered, and keep going until you end. I mean, if you can't find the appropriate node anymore, go back and look at an earlier iteration. Okay, so among the nodes that were discovered in the last round, which has the least degree, pick that node. Right, that is what H2 is. And it turns out that these are reasonable heuristics. In fact, H2 does beat change on many examples. But DQN does, the RL agent still does better than that. So here is what is happening. So looking at the betweenness, right? So the average betweenness score of all the nodes is 0.0152. The betweenness scores of the nodes that were queried by change for discovering the graph is 0.02. It's a pretty big jump. But then if you look at the RL agent, the average betweenness scores went up by another 50%. It's 0.0316. Right, so you can see that the reinforcement learning agent does learn to query things with a very high betweenness. And surprisingly, the same thing holds for degree as well. So this is B1. B1 is the homeless network, right? So the average degree of all the nodes is around 4, right? And change queries about 5.8. I mean, so basically the average degree of nodes queried by change is 5.8, but the average degrees of nodes queried by the RL agent is almost 8. It's 7.95. Right, and similarly, you can see that over time also, like every iteration, the DQN node, DQN does pick out nodes that are having high betweenness and high degree consistently. It's not just at the end, but at every step along the way, it does better than the other algorithms. Now, why is this surprising? It is surprising because the RL agent really does not have information about which nodes have a high degree. Right? Because it's just looking at the discovered graph. Right? So somehow the representation, remember I was telling you that we take the raw input and process it using a deep network for getting the state signal. Whatever is happening there is computing a representation that is implicitly capturing the expected degree of the node, not the current degree in the discovered graph, but the degree that it could potentially have later after the graph is fully known, right? And somehow that is happening, and we still haven't pieced out that part of the work yet. But still, we are doing some experiments on that. But that seems to be the only plausible explanation for why the RL agent is able to do so much better. Right. The same thing happens for the Israeli the retweet network as well. And again, both in terms of betweenness and degree, the RL agent is much better. Even though across iterations, it's not as clean a winner as it was in the homeless network. Right. So to conclude, so we have proposed a deep learning based method to learn to operate on graphs, right? And do things like structure discovery on graphs, right? So this is one thing we have used it for is looking at influence maximization on underscore social networks, but you could also do this for structure discovery in a variety of different contexts. And we are doing this on molecules and a bunch of other domains as well now. Right? And we observed between 10 to 36% improvement over change, which was the state of the art for this problem, right? And again, it is very interesting that we are able to pick nodes of high betweenness centrality with respect to the entire network, right? And hence our method performed better. So this is basically what, from the research point of view, this is the conclusion. I'll take a couple of minutes to address this one question that I keep hearing. Well, do you really mean to say that reinforcement learning can be used on real-world problems? Because we keep hearing that RL needs much larger volumes of data than even deep learning. And reinforcement learning works only in games where a detailed simulation is available, or is sure that RL is the solution that we should be looking for. So here are my answers to that. So RL needs a large volumes of data. If you run reinforcement learning very naively from scratch, yes, it might need a lot of data. But then there's so much work that has been done on, using historical data, looking at data augmentation techniques like we did with synthetic graphs, right? Or looking at domain models and then trying to enrich your learning by using models, right? Also, and looking at things like multitask learning, transfer learning, continual learning, and so on and so forth. There are many techniques by which you can reduce the data requirement for reinforcement learning or the experience requirements for reinforcement learning, and given the power of the problem formulation, right? So we really need to go that path, right? It's not like we can't just abandon it saying that, oh, we need many iterations for training, but we should figure out how to get it to work. The second question is RL works only when a detailed simulation is available. It turns out that you really don't need very realistic simulation. In fact, some of the simulations that we were doing were not that realistic. And also, even if you have past data, I mean, rollouts are often enough, right? So just replaying the past is quite often enough for you to get a very good policy. And then you can go ahead and try to deploy it in real problems, right? So you really don't need realistic simulations in all problem domains, right? So final thoughts. So we have building blocks to use reinforcement learning for real problems, right? But we really need to, as a community, we need to have concerted effort to widen the scope of RL. But I'm very excited about this, and so I would say that we have to now put reinforcement learning to work. Time for fun and games is past. We shouldn't just play Atari games, things like that. Try to find real problems and solve them. But then ML has a fundamental problem, and reinforcement learning really doesn't address that. Oops, I need to go back. Sorry. So ML really still learns association from data, and RL is also doing that. So we really don't have any knowledge of the structure or the process of the world, and we really have an understanding of a two-year world. So here is an example, right? So of an adversarial attack on RL, but still you can see how stupid it is, right? So now the agent is able to score goals, right? It's learned the blue guy is really good, right? Now look at what the red guy does. Oh, he just lies down on the ground and cries, and the blue guy now starts tap dancing instead of kicking the ball into the goal, right? So it's a very fragile policy that can easily be broken. Of course, there are now, it's like an arms race, right? People start looking at how to fix this. But the point is the whole situation looks very silly to many of us, right? So it's a long way to human-like performance. But in the meanwhile, you have to handle all the ML AI things with care, because it's not like any other 2-year-old. It's something like this that actually causes significant damage if you don't use it properly. So as I mentioned my course in the beginning, in fact, if you go to my webpage, the courses, it's actually available there. And I also have a much shorter tutorial because the course is 12 weeks course. I have a shorter tutorial that I gave at Purdue last year, and they have it hosted with all the video, the slides and other things synced. So it's actually very nice. So I'll stop here. Well, I have a bunch of slides about our center. Okay, give me 2 more minutes, Ajay. I'll finish up those slides as well, and then we can have questions. Is it fine?
Yeah, sure.
Yeah, great. So we have this Robert Watt Center for Data Science and AI at IIT Madras. So we do a lot of fundamental research, and especially deep learning networks, RL, and learning with partial data and ethics, fairness, explainability in AI, causal modeling, and so on and so forth. We do a lot of work in various verticals as well. And we have several education programs and programs of societal impact. And so we have a lot of collaborators, but more importantly, we do a lot of very interesting socially relevant projects. Like we help the ambulance service in Chennai respond more quickly, and looking at how to do the dispatching and routing and so on and so forth. We work with Google and the NGO called Arman in trying to improve maternal health. The same thing with they have a project funded by Bill and Melinda Gates Foundation where they're looking at preterm birth prediction and trying to build India-specific models for predicting preterm births, and a variety of different socially relevant projects. We do have a lot of activities in terms of the various kinds of research outreach, right, and workshops and so on and so forth. We actually did 2 fairly large online workshops already this year, and summits and so on. So I urge you to look at our webpage. So we have many fellowships by which you can associate yourself with the center. Like we have postdoc fellowships, post-baccalaureate fellowships, and research experience programs and things like that. So do take a look. And so that's our webpage. And so any questions about the center or about the work, welcome now.
Okay, thank you, sir, for the great talk. Felt it was a very interesting approach, an application for reinforcement learning for graph discovery. So we'll move to the Q&A now. I'll first cover the questions that are relevant to the paper, and then we'll move on to more general questions. So the first question is, how do you model influence in the network? Is it a binary variable or a stochastic variable?
So the influence itself is binary. Either you're influenced or not influenced. But whether a neighbor influences you or not is stochastic. Right. So when a neighbor gets influenced, you basically toss a coin and decide whether he's going to influence another neighbor. The model that I showed you in the beginning was a very deterministic model, but that's just for illustration purposes. But the actual model that we used here was a stochastic correlation.
Right. And the question also asks if the influence is probabilistic, then would an attention-like mechanism be something to consider?
Where would the attention play a role, right? So because when I'm doing network discovery, right, I just that's the part where I'm using reinforcement learning, right? So at the end of it, the reward that I'm going to get is like an expected influence propagation score, right? So it's only the reward process where the whole probabilistic mechanism goes in. It's not entirely clear to me where the attention mechanism would help while doing the influence learning. But there are other places where we are seeing this graph attention networks are helping, especially in things like molecule generation, stuff like that. If you drop a mail separately, I can talk about that.
Yeah, and that relates to the next question. So there are a lot of problems which can be modeled as graphs, like as you mentioned, molecular generation, and also discovering architectures of whatever neurons in the brain, and etc. So do you think a similar network discovery process can be applied to such problems, like drug discovery also? Actually,
Yes, we are doing it. Yes.
are you working on it? Okay.
Yeah. Not just us. I mean, there are a bunch of other places where people are doing it, and a lot of combinatorial optimization problems can be also modeled as graphs. And there are many real world problems that reduce to this kind of combinatorial optimization problems, right? So, for example, something like register location in a compiler, right? That's a graph coloring problem, right? So people have tried to look at using reinforcement learning for solving things like graph coloring, TSP, and so on and so forth. You could use graphs there as well. I mean, you could use this kind of technique there as well, right? So yeah.
Okay.
So
So
I want to answer this question. How do you treat RL problems where the action space is huge, right? So there's a lot of work that is happening nowadays on action embedding. So exactly like what we did here, right? So we didn't we did action embedding because our actions keep changing. The number of actions are not constant, and for every state you have different number of actions, right? And therefore we couldn't have a fixed architecture. So what we did was we basically did an embedding for the action and fed that in, right? But the action space is huge. Also, you could do that. Just like you have a vectorized representation for the state and you do generalization over that, you could have a vectorized representation for the action and do generalization over that. Right? There's a lot of work, interesting work, especially coming out from this guy Yash Chandak in UMass Amherst, right? So he works with Phil Thomas. So Yash used to be an intern with me, but he's doing some fantastic work at UMass now. So look up some of the action embedding stuff that's coming out. Really cool stuff.
okay, sure.
And RL is the method for doing continual learning, boss. I mean, there is a whole bunch of papers out there. Start looking at it, right? I mean, recently there are quite a few papers have come out of Mila, and then there is a guy Eric Eaton who is at UPenn who's been doing a lot of work on using RL for continual learning, and same thing with folks like Chelsea Finn and Sergey Levin from Chelsea is now at Stanford, but those guys also do a lot of RL for continual learning stuff.
I also want to ask you a question now.
Yeah. Okay.
Because I know you've worked a lot on hierarchy and hierarchical RL in the past.
Yeah.
So I was
No, I
wondering.
still do. I still do. My last paper was on hierarchical RL. Yeah.
Oh,
Like
great.
ECML
Okay.
2020. Yeah. Go on. Yeah. Go on.
Yeah. So I was wondering, like, the research on hierarchical RL seems to
Mhm.
have slowed down a bit over the past few years. So what are the open challenges and problems that you think are there in the field?
There are lots, right? So I mean, so the
Yeah.
point is, so one of the things we tried in the uh, uh, in hierarchical RL recently, our last paper, right, was essentially trying to address this problem in option discovery, in hierarchy discovery, where if you use any kind of data-driven approach to doing hierarchy discovery based on like the connectivity of the MTP and so on and so forth, you end up generating too many options. And then what people do is use some kind of a post hoc pruning, right? Or if these two hierarchies look very similar, then pick one, don't pick the other, and so on and so forth. And we said, hey, that seems to be very ad hoc, you know.
Hmm.
So what we do is we basically learn a kind of an encoder architecture for hierarchies. So you go ahead and discover how many ever things you want, but then you feed it through this encoder architecture so that it kind of groups all the similar ones into
Right. Right.
the equivalence classes and gives you one policy for each. Right, so that's one problem that we looked at. So the main open problems in hierarchical RL are, hey, where does the hierarchy come from? That's a big open problem that's been there for a long time. And the second thing is, how do if you're going to discover hierarchy, how do you come up with these neural architectures that can handle this kind of growing hierarchies? Right, the size has to keep growing, right? So is there any way that I can do transfer learning? Do I have to pause everything, start on a new architecture, or do I have to do some kind of distillation to go to the new architecture? But all of these are interesting questions. People don't have good answers to it. Right? In fact, even the very simple control architecture for hierarchies, like learning with 2-level hierarchies or 3-level hierarchies, how do you do the control thing, right? I mean, there are things like hierarchical DQN and all that which are severely limited. They don't scale well, right?
Okay.
And so that itself is a big challenge, especially when you come to the DRL space. So there's a lot of work to be done in getting hierarchies to work with deep RL. And so we've been working on a bunch of different things, and so are a few other people in the world. But I think the next few years, maybe the next year or two, we're going to see a huge glut of hierarchical, deep hierarchy clarifiers.
Okay, that's great. We have about 5 minutes left, so you can probably go through some other questions if you're able to see them and pick
Okay,
out
I
ones.
answered one. I can answer two. Yeah, I mean, you can use RL when when the outcomes of your actions are stochastic, right? And in fact, this particular case, the graph discovery case, we formulated the actions as deterministic. Once you decide which node you're going to query, that node has to give you the right answer, right? We could also model it as if the node would do this kind of in a stochastic manner. Maybe it'll pick some 60% of its neighbors and report you, right? No, the challenge in this particular case would be that you might have to query the node again. Right now, we assume that once you query the node is discovered and you move on, right? But that might not be the case always. And but you might have to do a little tweaks. But RL as a framework, right, is very much geared to handle stochastic outcomes of actions. Right? In fact, if you look at many of the like this, StarCraft and Age of Empires. Did they play Age of Empires? No, something else, right? So all of these things, right? So all these games have stochastic outcome because as soon as you have a second player in there, that's stochastic outcome. Right? So in fact, even in tic-tac-toe, if your opponent is random, if I put an X doesn't mean the opponent will put a O in the same place.
Yeah.
Right. So the outcomes are stochastic and it will still handle it. Yeah. Yeah, reward engineering is something that we don't pay enough attention to when you're solving real world problems. Reward engineering is something that is important. I mean, so when you're talking about AGI, you can talk about the most sparse, most minimal reward there is, and somehow we should learn from that. But when you're talking about using reinforcement learning to solve real problems like logistic problems or like this one, then you have to do some kind of reward engineering, but we don't pay enough attention to it. Yes, tree search. I mean, look up literature. In Monte Carlo tree search is something that has been embedded into many RL mechanisms, right? And okay, I can't parse the next question, but then look it up, right? MCTS. I mean, if you look at the original AlphaGo paper, that also has a lot of research rolled into it. And in fact, David Silver's PhD talks about something called TD search. There's an algorithm that has a tree search in part of it. That's the reason AlphaGo. Basically, he took TD search and put a deep learning wrapper around it, and made it into AlphaGo.
Right. Okay.
Yeah, RL and robotics have been working together for a long time. I think that's the last question. RL and robotics is well, if you believe the Berkeley people, they are the first people to have ever used reinforcement learning for robotics. But Peter Stone and others have done this long time ago. Chris Atkinson has done this. Stefan Scholl has some wonderful work on RL and robotics and stuff like that. And of course, people are doing deep RL and robotics now. So again, Sergey, Peter Abel, and Chelsea, and all these people. And same thing with the Austin group and UW. There are people who are doing this. Yeah, I mean, a lot of groups around that use RL for robotics, but it's been around for a long time. In fact, there is a chapter in my thesis where I used RL on a humanoid robot.
Okay.
this was 2003, 17 years back. Yeah.
Okay. So yeah, I think we're out of time. So thanks a
Yes,
lot
sir.
for
Thank you.
taking time off to be a part of our event.
Thank you, and good luck with the rest of the event as well.
Sure. Thank you.
Okay. Yeah. Bye.
Bye.
How do I leave the meeting?
There's a close video.